Welcome back to ECE 320A. This is video 2.3, and as a reminder, we're in Unit 2, which means you need to be working on homework number 2, and this material should be helping you with that. And at the end of homework 2 will be exam number 1. And all of this is still in Chapter 10 of the textbook, and today what I want to do is work through the complex power expressions or some different ways of writing the complex power expressions. One, when we only know the current going through an element or a set of values or impedances, and another one is maybe when we know the voltage that's dropped across those impedances. We've already looked at this or seen this occur or arise in a previous video, but let's just go ahead and derive these because they're not that difficult to derive, but it's helpful to have all of these different possible ways of finding the complex power because it depends on a particular situation what might be more useful to be using when we're trying to find different complex power values. Here, let's start with looking at the formulas when we only or when we restrict our attention to having access only to the current. And all of these are coming from exactly the same expression, which is the complex power formula, which says that that's now the voltage phasor in RMS, because we don't have any factors of 1/2 floating around, times the complex conjugate of the current phasor. And we said in this particular piece, we want to only assume that we have access to the currents, which means we need to rewrite the voltage in terms of current. And that's now doable by applying our knowledge of Ohm's law in a general form, which says that the impedance times the current flowing through that impedance will give us the voltage dropped across that impedance. So V phasor is Z, which is a complex number generically, times I RMS times the complex conjugate of the current. And as we derived last time, we now know that the product of a complex number times its conjugate gives us the magnitude of that complex number squared. So we have another way of writing the complex power formula in terms of currents, and that's now Z times the magnitude of the current phasor squared. We can also rewrite this complex power formula by expanding or identifying the impedance a little bit more finely. So we could write this complex power as R plus JX, where we have the reactive component and the real part, or the real and imaginary part of the impedance, times the magnitude squared of the current. And now we can find in rectangular form that the complex power is the real part, which is the resistor, times the magnitude squared of the current, plus J times the reactance, X, times the magnitude of the current squared. So that now we have the real part, or the real power, which is P, and plus J Q, there's our complex power, and now we've parameterized the real power as R times the magnitude of the current squared, and the reactive power as the reactance X times the magnitude of the current squared. Or we now have the power is I RMS squared times R in watts, and the reactance Q is now I RMS squared times X, volt amperes reactive. And we can do the same analysis just focusing on having access to the voltage. And these I will then label as the voltage formulas. We start exactly where we started before. We have the complex power, again, is just the voltage phasor in RMS times the current phasor conjugated in RMS. And now the distinction, or what we want to keep track of, is the fact that we only have access to the voltage. So now we have to replace the current in terms of a voltage formula, and the current now is just V RMS over the impedance, but we need to conjugate that so that now we have the complex power written in terms of voltages is V RMS times V RMS conjugate all over the conjugate of the impedance. And we know what a complex number times its conjugate is, so that now we have the complex power of a, let's say, a load that has an impedance of Z, written in terms of voltage values. We have the magnitude of the voltage across that impedance squared divided by the complex conjugate of that impedance's value. And that, when we do the algebra or the manipulation, will produce the complex power for that particular impedance.